A mile is defined as the distance a man walks in 1,000 paces. But which man? Me? Somebody who's 4 feet tall? The average man? What is the average man? And how come not a woman? Then they randomly changed it to exactly 8 furlongs, which is the distance a team of oxen could plow without resting. But which oxen? And how many of them? What if my oxen get tired more easily than yours does? Does that mean that your mile and my mile are different lengths? An inch is defined as the length of 3 barley corns. What the hell is a barley corn? Do I need to keep them in my pocket to line them up to measure things? And aren't all barley corns different? Which 3 barley corns are the right ones? It's also the width of a man's thumb. Which man? Me? The average man? Who is the average man? And how come we don't measure women? But an inch is also 1/2 of 1/2 of 1/3 of 1 foot. What's a foot? We'll get to that later. Fahrenheit was developed to make the boiling point of water 60, because 60 is easily divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Okay, cool, that's kind of how we tell time, I guess. This meant that water froze at 7.5 degrees, 1/8 of the way to 60. Well, that's kind of dumb. Then the inventor randomly rounded everything up and multiplied all the values by 4, making water freeze at 32 degrees, body temperature at 98 degrees, but water boils at 212, even though 60 times 4 is 240. Wait, what? The yard is defined as 3 feet. But what is a foot? You never answered that question. It's 12 lengths of 3 barley corns. But that's completely different from a half of a third of a foot. Yes, but a yard is also the length of a man's arm. But those are totally different things. Yes, but a yard is also defined as the length of a man's step. That's also totally different! And a nautical mile is 800 feet longer than a land mile. Why? A pound is 16 ounces. Okay, what's an ounce? It's a 16th of a pound. That doesn't help at all. Well, a pound is also the weight of a certain number of a certain type of old coin from England, like a shilling or a pence. Okay, well, which one and how many of them? Oh, it varies from place to place, and we actually have no idea. You have got to be kidding me. A cup is 8 fluid ounces. Wait, are fluid ounces and weight ounces similar? No, not even close. Well then why are they both called, and there are 4 cups in a quart? Why not 8? And there are 4 quarts in a gallon? No, why not 8 cups and 3 teaspoons in a tablespoon, and 16 tablespoons in a cup? I give up. So in all seriousness, this is why SI units don't suck. I'm going to be reading off of my screen because this is actually a lecture that I give in my science classes. The reason SI units such as, the meter, the kilogram, the liter, Kelvin for temperature, all that stuff, the reason that those don't suck is because they're based on physical world objects which don't have wild variances, unlike the width of a man's thumb or his step or whatever. A gram is the mass of water at its highest density. Now, it's kind of arbitrary to pick water, but it's extremely ubiquitous, it's important, we see it all around us, it works good. So a gram of water has a volume of exactly 1 milliliter, and the dimensions of a milliliter are the same as a cubic centimeter, or a cc. So we have mass, volume, and length all defined by this one object, and it does not alter. This isn't an SI unit, but if we take the calorie, a unit of heat, that's the energy required to raise the temperature of 1 gram, which is the same as a milliliter, which is the same as a cubic centimeter, of water by exactly 1 degree Celsius. So we have an actual logical method for measuring heat energy. The true energy unit is the joule, and a joule is the amount of work it would take to push a 1 kilogram mass object the length of 1 meter in a time of 1 second. Kilogram, meter, and second, those are all SI units. That force is also referred to as a Newton. If you apply a Newton of force over an area of 1 square meter, that's the Pascal, which is our unit of pressure for SI units. And a watt, like what light bulbs are measured in, a watt is 1 joule per second of sustained force. So a 60 watt bulb, while it is on, the entire time, it is exerting the equivalent energy of lifting a 60 kilogram mass 1 meter in the air in 1 second, which is a huge amount of energy actually. The other thing is that it's a base 10 system. So base 12 systems or base 60 systems, like what we do with time and kind of sort of how our calendar works or whatever, those are okay for dividing things in half multiple times or cutting them into thirds. But in science, we want to be way more precise than that. What's 4% of a foot? Nobody has any idea. You'd have to use a special converter, online calculator, or whatever to do that. But with base 10 systems, we can do that extremely easily. Now, is there such thing as a third of a meter? No, I guess not. It's 33.333 repeating centimeters. But to call that a weak point is very, very stupid. A meter contains 100 centimeters, which also contains 1,000 millimeters. A liter contains 1,000 millimeters, which is the same as 1,000 cubic centimeters, which is 10 by 10 by 10 centimeters. The kilogram is 1,000 grams, or 1,000 cubic centimeters of water. So a 1 liter bottle weighs exactly 1 kilogram. At least the water inside of it does. A metric ton is 1,000 kilograms, which is not 2,000 pounds. That's called like a short ton or something like that. But that's the equivalent of 1,000 liters of water, or exactly a 1 cubic meter sample of water would weigh 1 ton. Water has a density of exactly 1 gram per centimeter cubed, which is the same as 1 kilogram per liter. So those things scale up to each other perfectly. If we do this with imperial units, water has a density of 0.9587 ounces, weight ounces, per fluid ounce, which is really a completely random number. Then if you scale it up, well, we go from the ounce to the pound, and we go from the fluid ounce to the quart. It goes from 0.9587 for the ratio to 2.0875. There's absolutely no logic here. It does not follow any kind of pattern, because each system is totally arbitrary of the last one. So if I gave somebody a problem like how many inches are in 3.856 miles, well, here's how we have to solve that. Take 3.856 times 5,280 and then take it times 12. There. Nobody can do that intuitively. Absolutely not. But if I ask you how many meters are in 3.856 kilometers, it's 3,856. All we have to do is slide our decimal point around. Now, these are really simple examples. I mean, lately in my chemistry class, we've been doing some pretty complicated equations where we figure out the energy change in a chemical reaction. And that is only possible and logical using metric systems, using degrees measured in Celsius, using volume and masses measured in grams and liters. And if we did this with imperial units, it would be so complicated that you just simply couldn't do it. So that is why imperial units suck and SI units don't. Thanks for watching.